Suppose that a population of minks. Does anyone know what a mink is?
Isn't it one of those things for his fur?
Ferret looking.
Yeah, that's the only thing. I don't even know what a mink looks like, but I know that they used to make mink coats.
I think it's like
Yeah, let's look up minks.
You guys swear it's one of those things from Phineas and Ferb. Little like smart thing that the alien shit around Phineas and Ferb. His name is Mink.
Can we look up what a mink looks like?
Yeah, I'm doing it right now.
Yeah, that's like God. It looks like a brown colored ferret. Oh, that's sad. You want to work out?
It's a little animal that looks like a ferret.
That's cute.
Okay. So this is where I should remind you, we only knew what minks were because we know that people used to wear mink coats. Oh, sad. Okay, here we go. So, it says, this is our dp/dt. All right. Now, are you guys ready? Now, it says that we are not solving this explicitly, and I just want to point out what explicitly means versus implicitly. Explicitly means that that was the times where we had an equation, a separable differential equation, and we separated it and we were able to solve for y. So if you get the y alone, that's when you were solving something explicitly. Solving something implicitly were the times where we couldn't get the y alone, so we just left a bunch of y's in the problem, and we called it good. So there's a difference between those two words. If you look at this problem, think about the problems that we've been working on when we're talking about populations. We usually were not plugging in a number for p for the population. Usually that was our y value, that was our outcome, right? We were plugging in a value for a lowercase t. We were plugging in a time. Are you guys listening?
Yes, ma'am.
So if you look at this equation is in terms of the outputs, not the inputs. The population, those are the answers that come out, right? If you think about it, dp/dt instead of like dy dx, the p is kind of like the y, the t is kind of like the x. Does that make sense? So these are outputs, not inputs. So we're saying we are not solving this explicitly. We're not solving for y, or in this case, we're not solving for p. But we can still figure out some things about the population in question looking at this. And the primary reason, or the primary way that we do that is we look at slope fields and what we know about slope fields and equilibrium solutions like we saw in the video last night. So if you want to find the equilibrium solutions for the population, you just need to factor this. That's how we do that. So how could I factor this trinomial?
No.
Yeah, I'm going to take out a negative p as the GCF, and that gives me p squared minus 7p plus 10. Okay? And then how does this part factor?
2 and 5 and 2.
So p minus 5 and p minus 2. So we have 3 equilibrium solutions. We have p equals 0. We have p equals 5 and p equals 2. Do you guys remember, based off the notes for yesterday, I'm going to turn to that. So here we had 2 equilibrium solutions here. We had an equilibrium solution at 0 and an equilibrium solution at 10. And what do we say about these equilibrium solutions? They're asymptotes. What's happening to the population when you are really close to the asymptote? It doesn't approach 0, but it's approaching the asymptote itself, right? So once the graph of the population gets really, really close to the equilibrium solution, the population stays the same. Does that make sense? So here, once you get to a population of 10, your population is always going to be pushing against that asymptote. It's going to stay about 10 once it gets there, right? If you think about this as time goes back this way, we wouldn't have negative numbers, but if your population is really close to 0, it's going to stay close to 0 because there's no minks to be repopulating anything. So your equilibrium solutions are the places where your population doesn't change. So we're going to say the population doesn't change if you have 0 minks. That makes sense. You have 0 minks. There's none to procreate to make more minks. So you just have none. Or do we say 2 minks? Is that the right units?
Yes.
Read the problem.
No. Two populations.
2,000.
2,000, yeah, it says that it's in thousands. 2,000 or 5,000, yeah, 2 minks would be weird. Or 5,000 minks. Okay, so what we're going to do is we're going to sketch a slope field. Now, think about what we knew of slope fields. So here we don't have x and y coordinates, but we have t coordinates and p coordinates, right? T is kind of like the x value, p is kind of like the y value. So if we are plugging in only y values, the x value does not affect anything. So that means that all of our rows are going to be the same. So when I plug in a y value, or in this case a p value of 1, all the ones all the way across are going to be the same because the t value doesn't change anything. If I plug in a 2, all those are going to be the same all the way across because the t value doesn't change anything. Does that make sense? So this slope field is actually not very hard to draw because we don't have to think about the 2 variables interacting with each other. We just have to know what happens with one of them. So I want you to grab your calculator. And we're going to go ahead and draw this slope field. And we don't have to go very far because we're just going to go up to 6. I want to see what happens if we go a little bit past 5. So we're going to do 6, 5, 4, 3, 2, 1. It's not quite evenly spaced. Okay. So if we plug in 0, you can plug it into the factored form or you can plug it into the original form. It doesn't matter. If we plug in 0, what is the slope going to be? 0. If we plug in 2, what is the slope going to be? 0. If we plug in 5, what's the slope going to be? 0. So those equilibrium solutions, and that makes sense, right? Because the derivative should be 0 at those points. The population is not changing. Right? The derivative represents the rate of change. The population at those numbers is not changing, so the derivative should be 0. Right? Okay. So let's go ahead and plug 1 into that equation. So you can type it in however you want. I'm going to do -1 times 1 minus 5 times 1 minus 2. Our slope there is -4, so that's pretty steep negative slope here. Does it make sense how I'm drawing the slope field? Okay. I'm going to go ahead and plug in 3. So 3, 3, 3. Positive 6. There's a positive slope that's pretty steep. I'm going to go ahead and plug in 4. So that's a positive slope that's even steeper, it looks like. More steep? Is it more steep or steeper?
Oh wow, that's very wide.
Yeah.
-24.
And then let's go ahead and plug in 6 and see what happens after you get past the equilibrium solution. -24. Whoa.
That's like a straight line.
Yeah. Yeah, might as well, but we know those straight lines are slanting down like a little bit. Okay. Now, we can't see it because we didn't do decimals on our slope field, but in between these two horizontal lines right here, this part would look like a logistic function where we would see slopes. We would see slopes that are kind of like this a little bit, and then like this, and then the steepest right in the middle, and then they would flatten out a little bit. And the reason it doesn't quite look like that is because we didn't do the decimals in between, so we're only seeing the steepest ones in the middle of the logistic function. Does that make sense, how we're seeing that? So really, in between these two lines, it would look like a logistic function. Okay, What happens to the population for values of p sub 0 between the equilibrium values? So we want to see what's happening if you choose a population value that is in between these points. If your population is between 0 minks and 2,000 minks, what happens to the population over time? It goes down. Do you guys see that? So this means if you look at this slope field, you guys, this is important. You got to understand how these work. If you look at the slope field, if I started off with a population of 1,000 minks, I would get on my slope field like this, and it would go straight down to 0. So what does that mean about my mink population? It can't survive. You start off with 1,000 minks, your minks are going to die off. Does that make sense? If you start off with 1,500 minks, what's going to happen? You're going to die off. Okay? So we're going to say if the initial value is between 0 minks and 2,000 minks, what happens to your minks? Population dies off. And so that could be for any number of reasons. It's probably that at that point there's too many like mink predators for the minks to be able to be like numerous enough to survive. Does that make sense? There's something that would kill them off. Maybe it's all the people making jackets. Who knows? No? Okay.
Do they have meat farms for that?
I'm not sure.
I'm pretty sure they do. Somewhere they have meat.
So what about if you start off with a population of 3,000 minks? What happens? It goes up. Does it go up forever? No, it's going to get up to how many minks? 5,000. And what happens when it gets there? It's going to level off, right? What about if you start off with a mink population of like 2,050? It's going to go up. It's going to take a little bit longer, right? It's going to take a little bit longer to go up, but then it's going to do the same thing. It's going to go up and level off. So if we say that our initial value is between 2,000 and 5,000 minks, what happens to the population of minks? Does it stay at 2,000 or does it stay at 3,000? No, it increases to 5,000 and then it levels off. So population of minks increases to 5,000 and then levels. Okay? What happens to the population for values that start off larger than the largest equilibrium value? So what happens if we start off with a population of minks that's 6,000? They die. So it does. Do they die forever and then go to 0? No. Levels off at 5,000. So what circumstance would make sense with that? Why do they die off if you have extra?
Not enough food.
Not enough food. Not enough what? There's too many minks. There's like an excess amount of minks. Lots of people are making jackets, whatever. So that's kind of like our carrying capacity is that part up there. So we're going to say if the initial value is bigger than 5, then the population of minks decreases to 5,000, and then it levels off. What?
Yes, I'm seeing. I just
All right. So why do you think the mink population behaves the way it does? I said the environment can only hold 5,000 minks for whatever reason. Resources, whatever, food, water, shelter, that sort of thing. Yeah. But what happens if the population is less than 2,000 minks? It dies off. There's not enough for them to continue living. So, but
So can we do this for humans?
Yeah.
Eventually we gotta die off. Honestly, I think the things die off is more sense. I feel bad.
So I will say, actually, I did a mathematical modeling class in college where we were taking things like, you guys know how when you were in Math 1, Math 2, Math 3, you looked at problems for projectile motion where you talk about like a pumpkin being launched in the air or a cannonball or whatever. And you always looked at two things. You would look at like how high off the ground it was and how much time had passed. And you guys acted like those were the only two variables possible. Well, in my college level mathematical modeling class, we said, well, there's actually other variables. There's like gravity is not constant. Gravity is not, we have a coefficient for gravity, but it's actually not the same everywhere you're at, so it depends on where you're at in the atmosphere. We looked at like air resistance, we looked at like all sorts of different things, and we ended up writing differential equations that have like 10 different variables to represent all the different things that come into play in projectile motion. But one of the things I learned in my mathematical modeling class is that when you do lower levels of math, you usually use an easier model to represent a complex situation because your brain is not like smart enough to handle more. But we said that actually most populations, we always talk about populations growing exponentially, which actually if you look back at a logistic function, exponential is only like the first part of logistic graph. So if you were looking at populations, it might seem like, yeah, an exponential model makes sense. But if you look at populations for real, they're always logistic models. And you can actually look at the population of the world and you can see that we're like hitting carrying capacity, where you can see we have already hit our part where we were increasing the most, and you can actually see there's been a leveling off. And you can actually calculate, like if you start to plug numbers in, you can calculate what the carrying capacity of the world is, and we're like getting close, which is really interesting. But that's what we looked at a lot, is like a lot of models that you use are not accurate because you're looking at exponential models and there's not an unlimited amount of resources. There's a limited amount, and so you're going to start to see there's a leveling off effect with things, which is kind of interesting. But yeah, so they actually said as far as math goes, logistic functions are actually like real life the most common function. We just don't really study them, which is kind of weird. Yeah, they're not very, it's partially because they're not super easy to study, which makes sense, but okay. All right, how do we feel about looking at these? Can we kind of see where the equilibrium solutions come into play? Can you guys see how the slope field works? You can think of it like pushing towards those equilibrium solutions. Okay.